Howdy, and welcome to an auxiliary lecture on a steady state device example. So in this example, what we're doing is we're calculating, we're essentially treating our steady state device as a work device, and we're calculating how much, what the changes in the properties of the substance are as it goes through some kind of a process. So the details of that process and the substance are provided here in the write-up of the example, where we have R134A. It enters a compressor at a given pressure and a state condition. We're told that it's at saturated vapor, which of course means that the quality is equal to 1. We're given the volumetric flow rate. Notice the units on the flow rate there are cubic meters per minute, and that the R134A leaves the compressor at 700 kPa. We're also told that the power that is supplied to the refrigerant during this process is 2.35 kilowatts. So what we need to find then is the temperature of the R134A at the exit of the compressor. Okay, so just to clarify, this is not an isentropic efficiency type example, but we don't know necessarily the details of what that isentropic efficiency is. We could calculate that if we were interested in that, and we may have a brief discussion about that toward the end of the example. Okay, so to start the solution of the example problem, I always like to start with a drawing. And so we'll go ahead and draw our control system, which is of course the compressor. So this is our compressor. And of course we have our inlet state, which we'll identify as I, and our exit state, which we'll identify as E. And then of course there's some amount of work transfer, which we're given the power, so I'll subscript that as W dot. And of course I'm drawing this in the positive orientation where the power is coming out of the compressor, but we know that this is a compressor, so the power is actually going to be going into the compressor. And so this here will be a negative number. We need to remember to account for that when we actually apply this to the first law. Now, of course, there's also the other energy transfer term, which is Q dot, the heat transfer. And again, this would most likely be a negative number, okay? But for this particular example problem, we don't necessarily know what that Q dot is. We're not told that it's an adiabatic compressor, but we're also not given any details about what that heat transfer rate could be. So we really only have the option to make the assumption that it is adiabatic. Okay, and I'll summarize that again for us in just a moment. Okay, so the other information, that's essentially our control system. And now, of course, I like to be able to write down the other relevant information that we have, right? So, of course, we can say that what we're really analyzing, right? We say that we're analyzing the compressor, but to be very, very rigorous, what we're really analyzing is the R134A, right? That's technically our control system. That the substance is really the control system. And I write this down largely so that we remember that we're dealing with R134A as opposed to some other substance like water or an ideal gas. We also have state information that we're given. So we know that our inlet state, we know properties at our inlet state. So first of all, our inlet pressure, PI, is given to us as 180 kPa. And we're told that we're saturated vapor, which is basically to say that our inlet quality is 1.0, right? So this is from the statement telling us that we are a saturated vapor. We also have information at our exit state. At least we're given one piece of information at our exit state. We're basically told that the exit pressure, PE, is equal to 700 kPa. Okay, so at state I is what we would call fixed. We have two independent properties at state I. State E is not fixed. We only have one independent property at state E, so we need to know some other information about the process in order to determine state E, the exit pressure. Okay. Now, there's one other piece of information that we're given at the inlet state. We're told that that inlet flow, the inlet R134A, has a flow rate of 0.35 cubic meters per minute. It's very, very important that we pay close attention to the units here because we're not told, for example, that that's a volume flow rate. It's only by virtue of the units that we know that that is a volumetric flow rate as opposed to a mass flow rate. And so, and because we're dealing now with a volumetric flow rate as opposed to a mass flow rate, it's important to specify that that's the inlet volumetric flow rate. Remember that the principle is conservation of mass, not conservation of volume, right? So mass will be conserved through the compressor, but because the R134A's density, or specific volume if you will, is changing through the compressor, then the exit volumetric flow rate will be different than the inlet volumetric flow rate. Okay, so the last two pieces of information that I like to write down when we're dealing with this kind of a analysis is to then say that our, just one moment here, I need to change our viewing angle here. So the last piece of information that I like to write down is details about the process, right? And so what we would say here, the only detail about the process is that we know what the compressor power is, W dot. That's given to us as 2.35 kilowatts. We remember that this is a compressor, so we include that minus sign, right, because it's a compressor. So this is now where we're accommodating that minus sign on our drawing. We just basically already recognize that that's a negative power. The power is going into the control system, not coming out of the control system. Okay, and then I also like to write down what it is that we are being asked to find, right? So by reading the statement, what we need to find is basically the exit temperature, or TE. Okay, so this is, at this point, all I've done is I've summarized the information that's given to us about the problem, okay? Now we can actually start to analyze. And before we do anything, we should think about the assumptions that are being made in our analysis, okay? So we now begin our analysis, and the first thing that we do is we write down our assumptions. And some of these assumptions, in fact, all of these assumptions are basically going to be implicit, right? Nothing in the problem statement necessarily tells us that we can make these assumptions, okay? So we're just using our engineering judgment to make these assumptions. The first assumption that we make is that it's a steady state device, right? So we have a steady state device, which means that we're going to employ all of the rules that we know about steady state systems in our analysis. The next assumption that we'll make is that we're going to neglect changes in kinetic and potential energy. Now, so these two assumptions, assuming that it's a steady state device and neglecting kinetic and potential energies, in real life, these are very reasonable assumptions to make. You will find in engineering, as you practice engineering, you will make these assumptions again and again and again, right? It's only in special cases, really, when we're not able to assume steady state. If we're, for example, analyzing a transient system, or when we can neglect kinetic and potential energies. Okay, of course, there are cases when you can't do this for either assumption, but those tend to be the exception as opposed to the rule. The other assumption that we're going to make that is probably not realistic in real life, but we really don't have much of a choice in the case of, trying to find our exit temperature, is to say that this is an adiabatic compressor. Okay, now again, we're not explicitly given any information in the problem statement to be able to account for what the heat transfer could be for this device. In real life, if heat transfer was a problem, we would insulate this device to try and minimize that heat transfer as much as possible. If that wasn't a problem and we needed to capture or to analyze or to determine what that heat transfer loss is, in reality, what we would actually do is, we would in fact use the information, or we would use instruments to fix for us the inlet and the exit state, as opposed to use the first law, which is what we're going to do, to solve for the exit temperature. In other words, we would be using the first law to solve for the thing that we can't easily measure, which is the heat transfer. We can't easily measure heat transfer rate from a device, but we can easily measure inlet pressure, inlet temperature, right? We have devices, instruments that allow us to do that, and also the same on the exit side. Okay, but for now, this is an assumption that we will have to make. Okay, so now we can, based on these assumptions, we can go ahead and start to analyze our situation. And the first thing that we're going to want to do is to essentially start with the first law, right? So if we start with our first law, and I'm going to write down the generic first law for a steady state system, right? So we can already make the assumption, or impose the assumption, I should say, that this is a steady state device, okay? Which means then that our first law equation looks like the following. We've got heat transfer, Q dot, plus the sum of our inflow, m dot I, times HI. We're neglecting kinetic and potential energies, so I'm leaving that out of the first law equation. And this is all equal to W dot, the power, plus our exit flow, the sum of m dot E times HE. And again, I'm neglecting my exit kinetic and potential energies. Okay, well, a few things. One, we're making the assumption that this is a adiabatic compressor, so our Q dot term we've already established is 0. The other item that we note is that we've established that this is just a single flow in, single flow out, so we can essentially drop the summations, right? So our summation term here and our summation term here, right? There's just single flow in and single flow out. So with those two pieces of information, adiabatic and single flow in, single flow out, our first law then takes the form of the following. We can say that it's now equal to m dot I HI is equal to W dot plus m dot E HE. Okay, so let's take a look at this and see what it can tell us. We know our inlet volumetric flow rate. Okay, so we can find m dot I, right? So m dot I can be found by knowing our inlet volumetric flow rate, v dot I, and the fact that state I is fixed. Because remember, in order for us to find that volumetric flow rate, right, this is basically v dot I is equal to the specific volume at state I times m dot I. And so we can find our m dot I by knowing the volumetric flow rate and knowing our specific volume at state I, which we know because state I is fixed, right? We have temperature and pressure at state, or excuse me, we have quality and pressure at state I. Okay, so that first term, m dot I, is known in our first law equation. HI is also known because state I is fixed, right? So for the same reason that we know the VI, we also implicitly know what HI is. So we know HI, okay? W dot is given to us, the power is given to us, and so that is known. M dot E is also known from conservation of mass. So from our conservation of mass equation, we know because it's single flow in, single flow out, m dot I is equal to m dot E. We already know m dot I from v dot I and state I being fixed, so we necessarily know m dot E. The only thing that we don't know in the first law equation is HE, right? HE is unknown. It's the only unknown variable in that equation, one unknown, so we can solve for HE. And then once HE is known, we then will have two independent properties at state E. Those two independent properties are the exit pressure that was given to us and HE, the exit enthalpy that we use the first law to solve for. Okay, so that's how we're going to go about this solution technique. So let's go ahead and start working on this, right? So we can, just to basically complete our analysis of the first law equation, we can go ahead and start to or manipulate that first law equation such that we can write it in terms of HE, right? So we can simply say that HE is equal to m dot I HI minus W dot divided by m dot E. Okay, so now it's just a matter of calculating all of these terms. Okay, so we already know, I already wrote down the equation about how to find m dot I, right? So using our volumetric flow rate and our specific volume at state 1, we can say that m dot I is equal to v dot I over our specific volume at state I. And so we can then say that VI, of course, is equal to our saturated vapor specific volume at a pressure of PI, which is 180 kPa. Okay, and I know that because my quality at state I is equal to 1.0, right? I was told that my inlet state is saturated vapor. Okay, so I can find out that VI. I can go to my saturated table for R134A, and I can look up that VG at a pressure of 180 kPa is equal to 0.11041 cubic meters per kilogram. And that, of course, is equal to VI. Okay, I got that table or that value from table A12 in case you want to look that up. Okay, so now I can go ahead and calculate what my mass flow rate is. So m dot I is equal to v dot I, which is given as 0.35 cubic meters per minute, divided by my little vi, which I just looked up in the table as 0.11041 cubic meters per kilogram. And then, of course, I like things to be in seconds, not in minutes. So this is times 1 minute for every 60 seconds. Okay, and so, of course, we see that our cubic meters cancel, our minutes cancel, right? This minutes here is in the denominator. And so what we're left with is that our m dot I is 0.053 kilograms per second. Okay, so that's m dot I. While I'm in my table A12, I know I have to look up HI, so I can go ahead and say that, of course, HI is just equal to Hg at a pressure of Pi, which is 180 kPa. And so when I go to table A12 to look up Vi, I might as well also look up HI. And I'll just write that down here, which is 242.86 kilojoules per kilogram. Okay, so we're nicely trucking along here, looking things up. Okay, so now when I go back to my first law equation, right, this equation that I have manipulated, right, so this is manipulated from the first law, I looked up, I calculated m dot I, that's now known. I just looked up HI, W dot was given to me, and m dot E I know because I know m dot I. They're the same. So I can actually just go ahead and plug this in. Okay, so I'm going to go to a new page here, and I got to lift this fellow up here to the top of the page, and we are good to rock and roll, I think. Just get this lined up a little bit better. Okay, so let me rewrite that equation for y'all. Right, so we said that HE is equal to m dot I HI minus W dot divided by m dot E. Okay, and now I can go ahead and start to plug things in. So this is equal to my m dot I, which is 0.053 kilograms per second, times HI, which is 242.86 kilojoules per kilogram, minus my W dot term, which is negative 2.35 kilowatts, which of course is a kilojoule per second. And this is all divided by m dot E, which of course is the same as m dot I, so this is just 0.053 kilograms per second. Okay, so I plug all of this into the calculator, and I get a number that is equal to 287 kilojoules per kilogram. And so now I need to figure out what, so I now have two independent properties at state E, exit pressure and exit enthalpy. And I now need to figure out where this exit state is. So to do that, I'm going to rely on my good friend, the TS diagram, right? So you remember doing this as part of exam 1. And so let's go ahead and look at I'll look at the TH diagram, not the TS diagram. And in fact, actually, I'm going to look at the pH diagram because I'm given pressure and I'm given enthalpy, or I'm using enthalpy to determine this, right? So my pH diagram looks something like this, okay? And I just will, arbitrarily say that this is PI, 180 kPa. We'll say that this is PE, 700 kPa. Okay. So exit state will be somewhere along that line. Inlet state is, of course, right here, because the other independent property that we're told is that I'm a saturated vapor at the inlet state. And I know from looking up in the table, I know what this value is. This value is 242.86. Okay. And so now the question is where is my exit state? Well, I know that my exit enthalpy, based on my first law analysis, is 287 kilojoules per kilogram, which is of course greater than HI. So I'm going to be somewhere to the left of this value here, right? I'm going to be moving in this direction on the h-axis. And so I can just, simply say, well, maybe this here is where 287 is, right? And so then that means that I am up here. My exit state is where these two lines intersect. So my exit state is here, which is, of course, rigidly in the superheated vapor region, which means to find my exit state conditions, I have to go to table A13 for R134A. Okay, so let's go to table A13. And when I go to table A13 and I start looking up values in the 700 kPa pressure subtable, right? So for the subtable of pressure equal to 0.7 megapascals, this is how it's listed in the table, which is of course equal to 700 kPa. I see the following. I see that for my various temperatures, I have different enthalpy values. And so at a temperature of 40 degrees Celsius, I have an enthalpy value of 278.57. And then for a temperature of 50 degrees, I have an enthalpy value of 288.53. Well, my exit enthalpy is 287, which of course falls between these two enthalpy values, 278.57, 288.53, right? So my exit state is 287. which means that my exit temperature is somewhere between 40 and 50 degrees C. Okay, so if you take a look at this data, right, and you see that the enthalpy value at 50 degrees C is 288.53 and your enthalpy is 287, and then at 40 degrees C it's 278.57, which is of course a large difference. You're basically 9 kilojoules per kilogram away from the enthalpy value at 40 degrees C, whereas you're a little over 1.5 kilojoules per kilogram from the enthalpy value at 50 degrees C. So if you want, you can certainly pull out your calculator and interpolate what your exit temperature is, but you can also just kind of eyeball it and say, okay, well, my exit temperature is basically somewhere around 49 degrees C, right? It doesn't have to be so precise that we get that temperature carried out to 2 or 3 decimal places, okay? So that's the final answer, and this is essentially where we can stop the example problem. Now, the one thing to note is, we could in fact calculate or look up what the entropy values are here. So I mentioned that I would have a brief discussion about the second law in relation to this problem, and I'd still like to do that because I think that this could be kind of meaningful for you. And so if we just very quickly take a look at our TS diagram, okay, so let me draw this out here for you real quickly. And so this is our TS diagram. And it's not so important that we know exactly where our initial temperature is. I mean, we can say, for example, that this is our initial pressure, PI. We know that our inlet state here is right on the saturated vapor line. We know that the exit pressure is higher, so we can say that this is our exit pressure, PE. Okay. And if I look up these entropy values in the table, so let me do that real quickly. So if I look up the entropy value of R134A at state I, I'm at 180 kPa, of course, and that entropy value, Sg, so Si, is equal to 0.93965. And then if I go to table A, so this is from table A12. And then if I go to table A13 and look up the exit entropy at 700 kPa, or 0.7 megapascals, I basically see that my exit entropy is, say, roughly about 0.99. And so, if this is our inlet state, going back to our TS diagram, this is our inlet state, then that means that our exit state, right, so if I were to draw the constant entropy line, just to give us a frame of reference, our exit entropy is greater than our inlet entropy, and so our exit state is somewhere up here. Okay, and then we can draw our process as follows. So the solid line is the process. Okay, and the fact that our change in entropy is positive likely means that this compressor had entropy generation. So if I take a look at the second law equation, we can say that delta S is equal to our heat transfer rate. So let me do this correctly. This would be delta S dot. Okay, and then we have our heat transfer rate Q dot divided by T. And we have then plus our entropy generation, S dot gen. Okay. We've already established that this term here is 0 because we're making the assumption that our analysis is adiabatic. And since delta S is positive, right, delta S is a positive number, that means that it's due to entropy generation, right? Because we know that S gen can only be greater than or equal to 0. Okay. Now, there's a few things. If we had done this analysis, and if we had found, so for this example, if delta S had been negative, less than 0, then that would have implied that S gen was less than 0, which means that the process is impossible. Okay. Now, you certainly can have delta S, right? So in general, delta S could be less than 0, right? So the second law says that only S gen, entropy generation, has to be greater than or equal to 0, okay? But it is possible for delta S to be less than 0. This can be true, right? Delta S can be less than 0 if Q dot is negative. In other words, if you have a heat loss from the system. Okay, so I just want to point that out to y'all so that you're able to remember that when calculating entropy generations or dealing with delta S's that might be less than 0. Okay, so this completes the example, and if you have any questions, please feel free to email me or stop by and see me in class. Have a good day.